Welcome to this video covering Chapter 5 of the Managerial Economics book. This chapter will cover the production process and costs. Part 1 is the production process. We're going to start with the theory of the firm. The theory of the firm describes how a firm makes profit maximizing or cost minimizing production decisions and how the firm's costs will vary with their output. So we'll discuss, given an output goal, what combinations of capital and labor will the firm hire in order to maximize profit or minimize cost, and how that firm's costs will vary if they choose more labor and less capital, or vice versa. There are 3 steps in this process of the theory of the firm. The first is to get a handle on the firm's production technology. When we study this, it's going to look a lot like consumer preferences. We're not actually going to get into how does a firm produce, say, a can of soda, right? But we are going to be thinking about the general concept. Do they use lots of capital? Do they use lots of labor? Or do they use some balanced combination of capital and labor? Next, we're going to understand the firm's cost constraints. So how much money will they have to spend to get the combination of capital and labor that they're going to use to produce that particular amount of output? We obviously want to try to minimize the cost of production for a given amount of output for the firm to produce. Then we'll look at the 2 in combination with each other, the production technology and the cost constraints, and we'll choose the quantities of inputs, i.e. the quantities of capital and labor, that will minimize the cost to the firm given the firm's output goal. So we're going to be looking at how much do they want to produce, what combinations of capital and labor should they hire in order to minimize the cost of production. When we talk about the production technology, we generally talk about something called the production function. The production function tells us how much output the firm can produce from different amounts of the inputs. We write the production function as Q is a function of, and then here I've got capital and labor. Those are going to be the key things we're actually going to focus on, capital and labor. But it could be a function of land, could be a function of human capital, right? Human capital are those skills and abilities that our workers have acquired, and certainly is a function of technology. For our conversation, we're going to think about technology as part of this step 1 here in the production function. Different production technologies are going to give us different production functions that we're going to be looking at in that production technology. Another term that we should define before we move too far here is something called the factors of production. These are the inputs used to produce a good or service. Examples, as we already talked about in the production function, land, labor, and capital. There is a difference between the short run and the long run production function. The difference between the long run and the short run is capacity. For nearly any firm, their short run production function has a fixed capacity. This is because in the short run, the amount of capital is fixed. In the long run, all inputs can vary. That means the capacity of the firm can vary. When we say capacity, we really mean how much output the firm can produce. So we'll start by looking at the short run production function, and then we'll move into looking at the long run production function. To discuss the short run production function, we're going to assume a given technology, labor is variable, and capital is fixed. So we've got a few terms to define. Total product, or Q, is the quantity of the firm's output. I think the book might use a capital Q. I'm using a lowercase q. Really doesn't matter. We just know Q is quantity, and in this case, the quantity of the firm's output. The average product is the output per worker. So we just define that as AP equals Q divided by L, where Q is the quantity of output and L is the number of workers. So suppose, for example, we have Hungry Helen's Cookie Factory, and they turn out 200 dozen cookies in a day, and there are 10 workers producing those cookies. That means the typical worker, the average worker, made 20 dozen cookies for the day. The marginal product is how much output changes when we add one more worker. The equation for that is marginal product equals the change in Q over the change in L. So for example, pretend we had no workers, we get no output. If we hire one worker, we get 20 units of output. So 20 units of output for that first worker minus 0 units of output when we have no workers, 1 worker minus 0 workers, always where you end up minus where you start, over where you end up minus where you start. We started out with 0 workers and 0 output. We ended up with 20 units of output over 1 worker. So that first worker, when we hire them, gets us 20 dozen cookies for that 1 worker. One of the key concepts in economics is the law of diminishing returns. When we say returns here, what we really mean is that marginal product. So as the firm adds additional workers, when the law of diminishing returns kick in, that means the marginal product for that next worker is lower than for the previous worker. So you could imagine in our Hungry Helen's cookie factory situation, when you have only 1 worker, they're having to answer the door up front, sell the cookies to the customers, go in the back, try to mix the dough, put the cookies onto the cookie sheets, get those cookie sheets into the oven. It's a lot of work for 1 worker, and they have to divide their time. So maybe when they're up front helping a customer, cookies in the back get burned, and so on. When we add that second worker, they can actually divide up the work. Remember that concept of specialization and division of labor. So one of the workers can focus more on the front of house, while another worker focuses more on the kitchen. When the front of house isn't very busy, the person working up front could come to the back and help crank out more cookies. Maybe they're measuring out flour, chocolate chips, those kinds of things, while the person in the back may primarily be focused or completely focused on producing cookies. So that first worker, we said, maybe gave us 20 dozen cookies when they're working by themselves. When we add a second worker, that second worker may actually have a marginal product of 30 dozen cookies. Because we're adding them and we've got this division of labor, we can crank out more cookies. That doesn't mean the second worker themselves is personally more productive or is cranking out more cookies on their own. It means that division of labor allows that quantity of produced to go up by 30 units because we've added a second worker. So this would be a marginal product for that first worker or marginal product for that second worker. But then we add a few more workers, and there starts to be less room in the kitchen. There starts to be fewer tasks that we can have them do. And maybe the marginal product starts to go back down to where when we add that next worker, we get a little bit more product, but not a lot more product. Or maybe even worse, they start bumping into each other and spilling trays of cookies. So we get to a point where we've added so many people in that kitchen that our marginal product has even gone into negative territory. Now, of course, a firm would not want to choose to hire another worker when all they're going to do is decrease the amount of output that the firm's producing. So this is the concept of the law of diminishing returns. I've got a table here that represents a short-run production function. I know it's a short-run production function because the amount of capital is the same no matter how much labor I have here. If I have a fixed amount of capital and technology, then I'm looking at a short-run production function. Now, let's calculate the marginal product and average product for this sample data here. I'm going to use this table of data to generate a couple of graphs for us coming up here, but I also wanted to be able to show you some of these calculations from actual data. We wouldn't have an average product or a marginal product for a unit of labor equals 0. However, if we get 1 unit of labor, we can begin talking about an average product and a marginal product. So average product, remember, is the quantity divided by the number of units of labor. So 10 units of output, 1 unit of labor, 10 over 1, or our average number of cookies is 10. 10 per worker. Well, there's only 1 worker. They made 10, so there you go. That marginal product is the change in quantity over the change in labor. So we ended up at 10. We started out at 0. 10 minus 0. We ended up with 1 worker. We started out at 0. 1 minus 0, or 10. That's not a big surprise. We added 1 worker. We went from having no output to 10 units of output. So the average product and the marginal product are the same here. That will not be the case when we're moving across the production function. It just happens to be for the first worker. When we add that second worker, what is our average product? Suppose when we hire that second worker, we actually have increasing returns here. So we now have 30 cookies for those 2 workers. On average, we're getting 15 dozen cookies per worker. How much did that second worker add? So we say, where did we end up? We ended up with 30 dozen cookies. We started out with 10. We ended up with 2 workers. We started out with 1. and that second worker was able to add 20 dozen cookies to production. Like I said before, that doesn't mean that second worker themselves is actually necessarily making more cookies. That's that whole Adam Smith pin factory division of labor concept, right? And we'll do one more calculation just so we can see how this works. We have 60 units of output over 3 workers. That's 20 units of output per worker. When we hire that third worker, what happens? 60 minus 30, right? Where we ended up minus where we start, over 3 minus 2. Our denominator here has always been 1. I intentionally set the table up to be very simple like that. So the denominator is 1 because 3 minus 2 is 1. We were only going up by 1 worker. We get 30 units of output when we hire that third worker. So I'm feeling like maybe even further division of labor. There's always somebody prepping a batter. There's always somebody putting them on the cookie sheets and putting them in the oven and taking them out of the oven. And there's always somebody up front. They'll do a little kind of shift around and help each other, but they're really good division of labor here. What happens when I hire the fourth worker, you'll notice that marginal product no longer goes up, but in fact, it actually starts to go down. This unit 4 here, when we hire that fourth worker, that's the point where the law of diminishing returns kicks in. At L equals 4 here, the law of diminishing returns kicks in because the marginal product of hiring that fourth worker is less than the marginal product of hiring the third worker. Now, you might be tempted to say we should stop hiring then when we reach 3 workers. But in fact, we might need to produce the additional units of output. So it's not the case that simply because the law of diminishing returns kicks in, would we stop hiring those additional workers. It just means we're not gaining as much from that additional specialization that we might have from those previous units of workers. Now I'm going to take this table and turn it into a graph where we have labor on the x-axis and total output on the y-axis. And we'll see the shape of this production function. It's pretty typical. And we'll also look at the average and marginal products. The top graph in this page is our production function. So this is how much output we get for each of those different units of labor. You'll notice initially the slope of this curve is increasing. Notice how it looks like it's kind of going up in an exponential fashion. Here, we actually have increasing returns. Those are those first few workers who are adding more and more to output as we hire each additional worker. We're gaining from that specialization of labor. But notice at point C, that slope begins to flatten. So once we reach point C, we're experiencing diminishing returns. The slope of that curve gets flatter. And actually, once we pass D, we have negative returns. So no firm would want to be over in this range. If you're looking at this graph and you're seeing some connection to the numbers that we were looking at before, there is actually a couple of interesting things to note. The first of those is that the average product is actually the slope of the line between the origin and any point on the curve. So we can rotate this around and see that slope getting steeper and flatter, how much output we're getting per worker changing based on the number of workers that goes into this production function. The marginal product is the slope of the tangent line, which really makes sense because we're looking at what happens when you hire the next worker. So we're really looking at the slope of this line at those given points. The firm may choose to be at any point along the line up to and including D. D is the maximum amount of output that the firm could produce given this level of capital and technology, but they would certainly not produce beyond D. For those of you that are math-minded, you'll notice that this increases, it breaks, and then it decreases. This function is a cubic function. Production functions often have this sort of cubic shape. You'll also notice a comparable shape when we look at cost functions, where they increase slowly initially and then increase more exponentially. That's because cost is inversely related here. When we're getting a lot more output for a few more workers, our costs aren't rising very quickly. When we're getting a lot less output for a few more workers, our costs are rising more quickly with that output. So let's look at the marginal and average product from the table that we had before. This is looking at those in kind of a smoothed off fashion, but this is the general sense of how that looked. For one worker, we had 10 units per worker of average product. For 2 workers, it was at 15, 3 workers, and so on. Our marginal product went up more steeply and came down more steeply than our average product. This will always be the case. If there's increasing returns and decreasing returns, we'll always have this sort of increase and decrease, where the marginal product actually cuts through the tippy top of the average product curve. This might seem a little complicated, and that might be one of those things where you feel like you just have to memorize it. So let me give you an example that you can apply to your own life, something that will be easy for you to pick up on. I like to say that the marginal drives the average. We'll use the example of your grade in this class. Suppose that right now your average in this class is a 70%. We're thinking about the average here, right? That blue curve. The marginal would be the next assignment, right? How much will my grade change when I do one more assignment? We'll think about 2 examples here. Suppose that next assignment, you get a 90%. We all know what's going to happen. That will increase your average. Suppose instead that next assignment, you get a 60%. Again, we all know what will happen. That's going to decrease your average. That next unit and what you get for that next unit will pull the average up or pull the average down, depending on whether the marginal is above or below the average. Now we'll move on to talk about a change in technology in the short run, and what would that do to the production function. So I've recreated our graph from above and cleaned it up for us. And we want to look at a technological change, and what does that mean? We assume a technological change is a change in the technology that's going to improve the output. Otherwise, I would assume a firm would not adopt that technological change. So we'd say technological change is a change in the structure of production that increases output. Now, often when people think about a technological change, they think like, oh, you went from having normal computers to supercomputers. You went from being not very mechanized to very mechanized. All of those things are considered technological changes that could increase our output. But it could also be something like restructuring our management system. So I work for a professional services firm, which means I provide services to a client. We could decide to rearrange how we've got the work structured. So who's my manager? How do I report to that manager? How is the work managed? Those kinds of structural changes can increase the output of the firm. When we're looking at our graph below, an increase in technology would actually cause our curve to go up. And it's a little bit weird. You can't just say like a parallel shift, because we're going to still have, when we have 0 units of labor, we probably still have 0 units of output. No production process is fully mechanized where there's no workers at all. But this is going to have a similar where it swoops up, and then it's going to have a point at which it turns, and it's going to have a peak, and then it's going to go back down. So that peak might occur at some higher number of units of labor. Obviously, I didn't draw this dotted, but pretend that that's dotted out there. The turn here for diminishing returns was at 4 units of labor. That diminishing returns might not kick in until some later point. I'm hand drawing this curve, so obviously it's not great, but you get the idea here. That technological change is going to increase the amount of output we get for each of those units of labor. Now we'll shift our discussion to the long-run production function. We'll spend a little bit of time on this and also look at long-run costs, so that we can try to understand the firm's optimization decisions. I've made a very simple table here where we have the number of units of capital on one axis and the number of units of labor on another axis, because remember, both capital and labor can vary now. And the body of the table here actually represents the output. So when we look at 1 unit of capital and 1 unit of labor, that 20 there is how many units of output we would get if we employed both 1 and 1. This production function happens to take on what the book calls a Cobb-Douglas shape. And you'll notice that varying combinations of capital and labor can give us the same amount of output. So for example, 2 units of capital and 1 unit of labor gets us 40 units of output. Also, 2 units of labor and 1 unit of capital gets us that same 40 units of output. You also see if 1 unit of labor and 5 units of capital, we can get 75 units of output. 2 labor, 3 capital, 75 units. 3 labor and 2 capital, 75 units, 5 and 1. So in my mind, I'm kind of seeing this curve forming here between these combinations. In my table here, I'm already giving you a visual, in a sense, of what an isoquant is. I want to start by saying iso, quant, break it down into its Latin roots. Iso is same, quant, quantity, same quantity. So an isoquant is a line that shows the combinations of inputs that produce a given output. In other words, 2 units of capital and 1 unit of labor to produce 40 units of output, but also 2 units of labor and 1 unit of capital to produce that same 40 units of output. We can draw those isoquants onto an LK axis pair. So I'll map that first set of points. It was 1 unit of labor, 2 units of capital, or 1 unit of capital and 2 units of labor. And we have a curve that looks something kind of like this. It should look in your mind a little bit like an indifference curve, but this is an isoquant where the number of units that the firm could produce is 40. We could just map out one more here, and I'm going to change my color to red so that it lines up with the table that we had above. We had 5 units of labor, 1 unit of capital. Out here, we had 1 unit of labor, 5 units of capital here, and those combinations of 2 and 3 in the middle here. So 1 unit of labor, 5 units of capital, 2 units of labor, 3 units of capital, 3 units of labor, 2 units of capital, 5 units of labor, and 1 unit of capital. And those all happen to be on that same isoquant and give us combinations of capital and labor that would allow us to produce 75 units of the good. When I get multiple isoquants on my picture here, then I have an isoquant map, just like we had an indifference map with the consumer. An isoquant map is a set of isoquants for a given firm and technology. If we had a different kind of technology, then we might have different shapes of these curves. We might be able to put less labor and capital together to get that same amount of output. So along a given set of isoquants, we have a fixed amount of technology. Continuing to look at our isoquants, we want to define a term called the marginal rate of technical substitution. And I use the acronym for this, MRTS. I know, again, it looks a little bit like what we had with consumers, the marginal rate of substitution. This is the marginal rate of technical substitution, and we say technical because we're thinking about a firm producing with this much capital and this much labor, or this other amount of capital and this other unit of labor. It's technical, we're producing stuff. The marginal rate of technical substitution is how many units of one input can be given up when one additional unit of the second input is used, such that quantity is fixed. What I'm really saying is if I'm moving one more unit of labor into my production function, how many units of capital can I give up and still be on that same isoquant? So I still want to produce 75 units of output. How many units of capital can I give up if I hire one more worker? This allows us to start to get to the point where we can think about the cost of labor, the output of labor, the cost of capital, the output of capital, and start to get to a point of making a decision. We calculate the marginal rate of technical substitution as the negative of the slope of the isoquant, or negative change in capital over change in labor. So we'll look at my example here, point A to B, and we'll calculate that marginal rate of technical substitution, assuming that we're moving from point A to point B. So negative of, I started out at 5, I ended up at 3 units of capital, so 3 minus 5. I started out with 1 unit of labor, I ended up with 2, so 2 minus 1. I get negative 2 over 1, or 2. This means the firm can use 2 fewer units of capital when they hire that second worker, given that the firm is producing 75 units of output. This is going to come into play in our optimization question when we get to a point where we have that second step, the firm's costs, and we combine those two, this marginal rate of technical substitution and the production technology, with the cost to determine the optimal amount of capital and labor that the firm should hire. Before we move on to costs, there's a couple of other production function shapes I wanted to talk about, really relationships between capital and labor that we might face. The first of those that I wanted to discuss is something called fixed proportions production function, or a fixed factor production function. It could be called either of those. The book actually calls this a Leontief production function, which it is. This is the one where it has quantity is a function of the minimum of capital and labor. To define that in words, we would say inputs must be applied in a fixed ratio to produce the output. In other words, the factors of production are complements. They must be used together in order to produce the good or service. Say, for example, we have a production function where we have 5 workers to 1 unit of capital, and that gives us an output of 100 units. So let's put that point here, 5 units of labor and 1 unit of capital. It's going to give us an output of 100. But this is a case where we have to apply 5 to 1, and any ratio outside of 5 to 1 does not give us additional output. So we could hire 10 workers, 15 workers, and so on. If we only have 1 unit of capital, we're only going to get 100 units of output. The example in the book that they give is rideshare, where you have cars and drivers of those cars. You could have a bunch of extra cars, a bunch more capital, but if you don't have drivers to drive them, you don't have additional ride shares that you're able to pick up and generate revenue from. Similarly, if you have that one car and you hire a bunch more workers, you're not any better off because you're not going to be able to drive more cars. You don't have more cars. If I wanted to draw a second curve in here, I could do that. Let's change my color again. We'll make this guy blue. We've got 10 units of labor and 2 units of capital would give us a new production function. It would still look like an L shape. And I could draw that in here, pretend that's an L, and we get our new quantity. I don't know for sure that this is exactly double. It could be more than double. It could be less than double. We'll talk about that in a moment. The second production function I wanted to show you that was not like our Cobb-Douglas is perfect substitutes in production. This is the case where the inputs can be substituted for one another in some fixed ratio in that production function. This is the example where the book called this linear. And let's look at an example here. Suppose that we could substitute 1 unit of capital for every 3 workers. So this would look like the line below. If we have 15 units of labor and no capital, we could produce some fixed amount of output. Let's call this Q equals 100. If I substitute away from labor completely, I would need 5 units of capital to produce that same amount of output. And there'd be various combinations in between. If I had 4 units of capital and 3 units of labor, I could produce that same amount of output. I could draw in a second line here and we'd get a similar kind of relationship. So I'll put in our second production function here. And suppose this is 30 and this is 10. We could be at 30 units of labor or 10 units of capital or some combination in between. Again, I don't know how many units of output this is. It could be double, it could be less than double, or more than double of what we had with our other production function. We do know something for sure. The marginal rate of technical substitution here is 1/3. For each unit of capital I give up, I can get 3 more workers and stay on the same production function. The last concept I want to talk about before we do a practice problem is returns to scale. When we say returns, remember we're thinking about that product, how much additional output. When we think about scale, we want to think about the size of the operation. We define returns to scale as the rate at which output changes when we change the quantities of the inputs. I like to think about it this way. What happens to output when inputs are doubled? When we say double, we mean going up by 100%. So if I had 5 units of labor and 1 unit of capital, and I now have 10 units of labor and 2 units of capital, do I get lots more output, a little bit more output, or not very much more output? That's really how you can think about increasing constant and decreasing returns to scale. For increasing returns to scale, we say output more than doubles when inputs are doubled. So for example, if we have 5 units of labor and 1 unit of capital, and that gives us 100 units of output, and we double that to say 10 units of labor and 2 units of capital, we're going to get more than 200 units of output. Double would be exactly 200. So let's pretend that would be 225. This would be increasing returns to scale. For constant returns to scale, output exactly doubles when inputs are doubled. So we had 5 labor and 1 unit of capital. We get 100 units of output. For 10 units of labor and 2 units of capital, we get 200 units of output. So it's a constant increase. For decreasing returns to scale, we say output increases by less than double when inputs are doubled. So if we had 5 units of labor and 1 unit of capital, giving us 100 units of output, 10 units of labor and 2 units of capital would give us something less than 200, right? 200 would be double, so maybe something like 185 units of output. Now let's take those concepts and look at them on a graph. Suppose we have constant returns to scale. With capital as 4 units, labor as 5 units, we get an output of 20 units, as represented by my purple line here. Suppose we were to double. That would mean 8 units of capital, 10 units of labor. If we have constant returns to scale, we know then that we're going to have 40 units of output. So to graph that, I'm going to say suppose we're at 5 and we double that to 10. Suppose we're at 4 and we double that to 8. That point at 10 and 8 would be some point like this. I'm going to grab my curve and say, okay, this is where our new isoquant would have to be to have constant returns to scale. For increasing returns to scale, again, suppose we had 4 and 5, we would have 8 and 10 units of labor, but that would give us something more than 20 additional units of output. Say we would get 60 units of output. So I want to graph this, and it's actually going to look exactly the same as it does above, which is part of why I wanted to show you this. So 10 and 8, and I get a point on this curve, and it looks something like this. The difference is that this quantity is now 60. So if I wanted to talk about reaching a quantity of 40 when I have increasing returns to scale, I would actually be choosing some quantity of capital and labor that would be inside this green line here. Some lower amount of capital and labor would be my isoquant of 40 units of output. And again, sorry for the bad drawing, but you get the idea here. If I had decreasing returns to scale instead, that green line would represent something less than 40. So it'd be the same amounts of inputs, it's just the amount of output we're getting. And these surface lines here show us that amount of output. Now let's look at a sample problem. Suppose that the following function is a production function for a firm. Q equals 2 times L to the 1/2 power plus 5 times K to the 1/2 power, where Q is the number of units of output for the firm, K represents the number of units of capital, and L represents the number of units of labor. I've graphed an approximation of the first isoquant here, where the quantity equals 100, and this point 800 units of labor and 75 units of capital is on that isoquant. To start with, a simple question, I believe, is the production function that's given above in the problem a short-run production function or a long-run production function? Well, I look at this function and I see there's a term that has capital in it. Capital is allowed to vary. We know if capital is allowed to vary, this is a long-run production function. Now to a little bit more of a difficult question. Does this production function exhibit increasing, decreasing, or constant returns to scale? The easiest way to answer that question would be to plug in values and see what we get. We have a point that's already been provided for us. We know at 875 we get 100 units of output. So we could double the 800, double the 75, plug them in, and see if output is greater than 200. If it's greater than 200, it's increasing. If it's equal to 200, it's constant. And if it's less than that 200, we have decreasing returns to scale. So our production function is Q equals 2 times the number of units of labor. We're going to double our 800. So I'm just going to put it in as 2 times 800 so you can actually see this happening here. Raise that piece to the 1/2 power, plus 5 times 2 times the units of capital. I'm doubling my capital here. Also raise that to the 1/2 power. Then we really just have to do some basic arithmetic, and we can come to an answer. So 2 times the square root of 1600 plus 5 times the square root of 150. Remember, the 1/2 power is the same thing as saying the square root. So I get 2 times 40 plus 5 times 12.25. And this gives us a quantity of 141.25. Since this is less than double the output that we had before, we have decreasing returns to scale. So that was a simple way to do the math and just get to an answer. If we didn't have that point, we could have calculated a point like point A and then calculated another point just like we did and do that same sort of measure. The next question says, considering the answer from part B, draw in a very approximate isoquant that represents 150 units of output. This one takes a little bit of thinking here, but let's look at this. We doubled the inputs. We went to 1,600 units of labor and 150 units of capital, and we got 141 units of output. To be able to get to 150, we would need to be out beyond that number of units of labor and capital. So I put very approximate in here because I'm really just trying to get you to understand the concept of increasing, decreasing, and constant returns to scale. So I'm going to put that point on the graph just for the sake of reference. 1,600 units of labor and 150 units of capital was our double point. At that double point, we know the quantity was 141. So if I need to draw an isoquant that's out at 150, it would need to be something that lies out in the XY plane or the KL plane that's beyond that 141. Now, obviously, mathematically, this is probably not the correct point, but from an abstract perspective, we would know it would need to be somewhere out here where that red line is, beyond that green point. Part D of this question, what happens to the marginal product of labor as labor is increased when holding capital constant? Now, this one's a little bit more complicated, and often when I reach a problem that's complicated and I'm not quite sure where to start, I start by looking at what I know and what I don't know, and then I have to make some assumptions. So in this particular case, I'm trying to find out about the marginal product of labor. So I need labor to change. Capital is going to remain constant. What I can do then is assume capital is some value. So for the sake of argument, let's assume capital is constant at 1. So if we're going to look at k equals 1 in whatever scenario we're talking about. And we just need to see what happens to output when labor increases by 1 unit. So I'm going to start out with labor being 1 unit, and then I'm going to look at labor being 2 units. And just to be able to be sure whether the marginal product is increasing or decreasing, I really have to have a third point. I need to see between these 2 points, what is the marginal product? Then between these 2 points, what is the marginal product for me to be able to make a determination on what's happening with that marginal product of labor. So let's do the math here. So Q equals 2 times 1 to the 1/2 power plus 5 times 1 to the 1/2 power. And you can see why I chose 1, 2, and 3. It's going to be super easy to do the math. The square root of 1 is 1. So 2 plus 5 is 7 units of output. Then I'm going to look at 2 units of labor. So Q equals 2 times the square root of 2 plus 5 times the square root of 1. That part's going to stay the same all the way down. And if I do a little bit of math here, I'm going to get 7.82. So my marginal product between those 2 points is 0.82. When I hire that additional unit of labor, I get 0.82 more units of output. And we'll plug in 3. 2 times 3 to the 1/2 power plus 5 times 1 to the 1/2 power. And I'm going to get 8.46. My marginal product of labor for that third unit of labor is 0.64. As labor is increasing, my marginal product of labor is decreasing. So I have a decreasing marginal product of labor. That's also to say I have diminishing returns. There's one last part to this problem that I want to work here. Assume that the firm is continuing to produce at 100 units. What is the marginal rate of technical substitution when labor increases from 800 units to 850 units? So we're still going to stay on that goal production of 100 units, but we want to substitute away from capital towards labor. How much capital will we have to give up to add these additional units of labor? So to start with, we'd need to find out the quantity of capital that we'd have to have 850 units of labor and be right on that 100 unit isoquant. So we're going to find K when L equals 850 and Q equals 100. We'll use our production function. We'll say 100 equals 2 times 850 to the 1/2 power plus 5 times K to the 1/2 power. I don't know what K is. That's what we're trying to solve for. So we'll take the square root of 850 and we'll multiply it by 2. That works out to be 58.3 plus 5 times K to the 1/2 power. I'm going to subtract my 58 across, and I'm going to get 41.7 equals 5 times K to the 1/2 I'll divide both sides by 5, so k to the 1/2 equals just a little over 8. It's actually 8.34. And then I'll square both sides to get rid of the square root. And when I square both sides, I get approximately 70. It's just barely under 70, so this is good enough for what we're trying to do here. Now I need to calculate the marginal rate of technical substitution. So the marginal rate of technical substitution is negative of the capital we ended up at, which was 70, and we started out at 75. We ended up at 850 units of labor. We started out at 800. So we get minus 5 on the top, which is 5 over 50, or 1 over 10. So we're giving up 5 units of capital to get those 50 units of labor, or 1/10 unit of capital for each unit of labor. Thanks for watching part 1 of chapter 5. Come back for part 2.